thank you very much for coming, and thank you very much to the organizers of this conference. So I'll be talking about decompositions of a notion of complexity on tensors. In case you don't know that already, a tensor is a generalization of a matrix in a way, and the slice-wonk is a notion of complexity on tensors, and I'll be talking about both slice-wonk decompositions and the structure of slice-wonk decompositions for a given tensor. So first, I'll discuss a little bit what the main problem is. Then I'll mention the case of the tensor-wonk, which is substantially simpler than that of the slice-wonk, and then we'll go over the main difficulties and results. So throughout the talk, we'll take F to be a completely arbitrary field. The specific choice of field will not matter much, especially in the first half of the talk. At the very end, we'll take the field to be finite, but aside from the size of the field will not matter. So for now, you can safely, leave the field aside, and whenever the field becomes relevant, I'll mention it again. Now, it's well known that if you have a matrix of some specified rank, then all decompositions of that matrix with minimal length are the same up to a change of basis. So for instance, if you take a decomposition here, as in that expression, you can take linear combinations of the Fi instead of the Fi themselves, and this gives you new functions Fi and new functions Gi, so you can have it's possible to have more than one decomposition. But these decompositions are the same up to a change of basis, and there is a systematic way of moving from one decomposition to all decompositions. And in particular, there exist linear subspaces A1, A2, such that whenever you take a decomposition of the matrix, the linear subspace spanned by the functions in the first coordinate is equal to A1, and the linear subspace spanned by the functions in the second coordinate is equal to A2. And in particular, if the field is finite, then we know the exact number of decompositions of the matrix, because that number is the same as the number of bases of F to the K, and the number of bases of F to the K is the same as the number of linearly independent families with size K in F to the K, and that's the product of all these terms there, because for the first, you can choose the first element to be anything except the zero element. Then you can choose the second element to be anything except the line spanned by the first element. Then the third element to be anything except the plane spanned by the first two elements, and so forth, until the last element, which can be chosen arbitrarily as long as it does not lie in the hyperplane spanned by the first K minus 1 elements. And this product is approximately F to the power K squared times, so this product is exactly F to the power K squared times some product, but that product is always between, 1, obviously, that's the upper bound, and the lower bound is a constant, a positive constant that's independent both of F and of K. So that the number of decompositions is comparable to F, to the size of F to the power K squared. And we can ask whether these statements on the fact that a matrix of given rank has a bounded number of decompositions, we can ask whether this kind of statement generalizes to higher dimensional tensors rather than matrices. But of course, even before going into that, we have to define the analog of matrix rank for higher dimensional tensors. Now to define the notions of rank on tensors that we'll use, of course, we may think these notions will specialize to the matrix wonk in two dimensions. So we can first look at the matrix wonk, examine how it is defined, and try to extend that. So a matrix is just a table. So of course, it can also be viewed as a linear map or as a bilinear map, but for the purposes of this talk, we'll just view a matrix really just as a table. You have rows and columns, and then formally, this is just a function from the row indices times the set of row indices times the set of column indices, the text values in the field. Now a matrix is said to have rank at most 1 if we can write its entries as a product of two functions, where the first function is purely a function of the row, and then the second function is purely a function of the column. That's a matrix with rank at most 1. And a matrix is said to have rank at most k if and only if we can write it as a sum of at most k matrices that each have rank at most 1. And this is how the matrix rank is defined. Now, moving from matrices to tensors, an ordered tensor is in a way also a table, except that instead of just having rows and columns, you might have a third dimension and a fourth dimension, and you can have arbitrarily many dimensions. Okay, so an ordered tensor is a d-dimensional table, if you like. Now, the one important point is that for higher dimensional tensors, there is not one single canonical generalization of matrix rank. Instead, you have several notions of rank that are in a way competing against against one another, in the sense that the best notion of rank, so to speak, will depend a lot on the application that you have in mind and on the context of your specific problem. Now, these notions are different and do not behave in the same way, but they have similarities. Many of them have similarities. And the first similarity is that the way is that moving from tensors with rank at most 1 to tensors with rank at most k is done in the same way in the definitions, even though the sets of tensors with rank at most 1 are not the same. So once for a large class of notions of rank, once you have specified which tensors have rank at most 1, we say that a tensor has rank at most k if and only if we can write it as a sum of at most k tensors, each with rank at most 1. So that step is the same as for matrices and is the same for all of these notions of rank. Now, as I've said, the main place where these notions of rank differ is in the sets of tensors with rank at most 1. The following three notions are some of the most successful, some of the most popular, let's say. Although, of course, this is all a subject in its early days, but these three notions have been used a lot recently. In fact, the tensor rank, has been used now for several decades, and is clearly the oldest of the three notions of rank, and it's used a lot in computational complexity theory. So for the tensor rank, the rank 1 tensors are the tensors that you can write as products of d functions, where each function is a function in one variable. Or stated a little bit more precisely, the first function is a function in the first variable, the second function is a function in the second variable, the third in the third variable, and the dth function is a function purely in the dth variable. That's the tensor rank. Now, in 2016, Tao introduced the slice rank while reformulating the breakthrough of Put, Levpar, and then Ellenberg and Jesuit on the capset problem. In the case of the slice rank, the rank 1 tensors are the tensors which may be written as products of two functions, where one function is in one variable and the second function is in the remaining d-1 variables. And then the third notion is the partition wonk that Naslon defined 1 year later in 2017, again, in the context of combinatorial problems. In his case, he wanted to obtain existence results on k-right corners. And there, the rank 1 tensors are the tensors that, yet again, can be written as products of two functions, where one function is in sum, but in some of the variables, but at least one of them and not all of them. And the second function is in all remaining variables. Now, in this talk, I'll discuss the tensor rank and the slice rank, and the analogs of the results that I'll discuss are not at least yet known in the case of the partition rank. Now, remember, in the case of matrices, we had said that for a matrix with fixed, for whenever you had a matrix of some fixed rank, and you wanted to obtain rank decompositions of that matrix with the same length as that rank, the only way you could do so was to make a change of basis on your original decomposition. And that, in particular, as a result, you had common linear subspaces that systematically contained for any decomposition all your rank functions in the relevant coordinate. Right? Remember, we had these subspaces A1, A2. Now, in the case of the tensor rank, a tensor might have more than one tensor rank decomposition with minimal length. Even if we allow changes of basis, there can be more than one possible decomposition. But something that does remain true is this consequence about subspaces that we had in the matrix case. This remains true. If T is an order D tensor with tensor rank, let's say K, then then there exists linear subspaces A1, A2 up to AD, which are fixed and common to all minimal length decompositions of the tensor, such that whenever you take a minimal length decomposition of the tensor, the functions in the first the linear subspace spanned by the functions in the first variable is equal to A1, and similarly for the other variables. And this, by the way, gives you in particular a bound on the number of possible minimal length tensor rank decompositions in the case where the field is finite. That number is at most, the size of f to the power d minus 1 k squared. So you might ask, why is it d minus 1 and not d in the exponent? That's just because when you write a decomposition like this and you look at the product, a2i times a3i times adi, these are linearly independent, because if they were not, then you would get a decomposition with smallest length. So once you fix these products, this forces the choice of the A1i. But that's a somewhat minor point. The main point is the consequence about the subspaces A1, A2 that we had in the matrix case extends to the tensor rank case, even if there may be more than one minimal length tensor rank decomposition, even up to change of basis. Now, right, so how would one go about proving this result? So suppose that the tensor T, has tensor rank K, and we write two minimal length decompositions with length K, as I have done at the top. So as I wrote on the slide, to prove the first conclusion, meaning that we have this spanning here with that we have A1 be the linear subspace spanned by A11 up to A1K, and similarly for the other ones. To prove that, it suffices to show that for every choice J of coordinate, the linear subspaces aj1 up to ajk, and the linear subspace bound by aj1 dash up to ajk dash are the same. So assume that they assume, that they are not the same, then how could we get to a contradiction from that? So obviously, because the situation is symmetric, we can suppose without loss of generality that the linear subspace, that the first linear subspace, is not contained in the second linear subspace, and that's the main technical point of the proof. This means that there exists a function, from the set of rows, let's say, first coordinates. So there exists a function u such that u has inner product equal to 0 with all the functions a1 i dash, but has at least one non-zero inner product with one of the functions aij for some j. So so all the u dot a1 j dash are 0, but at least one of the u dot a1 j is not equal to 0. There exists such a function because of the absence of inclusion between the two subspaces that we just described. And applying the function u to both decompositions of T that I started with, meaning taking the inner product with the function u, that is, summing over all the xi, so sorry, over all the x1. We get for the first decomposition, we get the expression that I wrote at the bottom. So because u is purely a function in x1, we can just rewrite the expression we started at the top like this. We can put parentheses around u dot a1i, and the remainder of the expression is unchanged. And we can do, of course, the same for the second decomposition, but using that all of these inner products u dot a1i dash are 0 for the second. We get that when we apply u to the second decomposition, we do get the 0 tensor, and therefore this provides the inequality that we have at the bottom. This provides the equality that we have at the bottom. And because all the parenthetical coefficients are non-zero, this means in particular that all the products a2i times a3i times up to adi are not linearly, they're not all linearly independent. And this contradicts that this is a minimal length decomposition. This contradicts that the first decomposition at the start is a minimal length decomposition. So that's the first conclusion, and the second one, so the one we had at the bottom of the slide, then why the number is at most that, as I explained a few minutes ago, that's because once you determine the products, that's again the fact that once you've determined the products a2i times a3i up to adi, then this determines the functions a1i because of this linear independence. Right, so here what I've written is the details of why you get a contradiction if you have if you don't have linear independence. It's because if one of these functions is a linear combination of the other ones, then you can write, as I've said, a tensor composition with smaller length. And how do you write it with smaller length? It's because you just have these new functions, capital A 1i. Right, so That was the case of the tensor bank. Let me now move to the slice bank. And as usual, we can start with, we can wonder from a decomposition, how can we build new decompositions as we did for matrices. So for matrices, we had changes of bases, and for the slice walk, can we do anything else, or can we do anything at all? So first, yes, we can do something. At least in a way we can do at least what we can do for matrices, because a tensor bank decomposition is a decomposition of that kind here, as I've written in the first equality. So in a way, this each of the three parts of the expression, you can view it as a matrix where we've merged two of the coordinates. So for instance, the first part, you can view it as a matrix where the rows are indexed by x, and the columns are indexed by the pair y times z. But you can view that first contribution as a matrix, as a two-dimensional tensor, and likewise for the other parts. And for matrices, we know that we can use changes of bases to rewrite matrix decompositions. And if we perform that on any of the three parts viewed as a matrix, then this gives you a new decomposition of the original tensor. So this is saying that in a way you have at least as much room for new decompositions as you do have for matrices. And of course, here you have three matrices, so this gives you even more flexibility, because even changing just one of the matrices gives you a new decomposition. But of course, you can modify them simultaneously. Now, here, what I've in doing that, one potential flexibility that we have not used is that the three contributions here are the same when we do these operations. They remain the same even though the decomposition itself has changed. The three contributions remain this. I mean, the total of each term remains the same, even though the decomposition within the term is not the same. But it's also possible to change these three total contributions. So here's an example in which this is particularly clear. Say that you have a tensor that not only has slice rank k, but also has tensor rank equal to k. So suppose that the slice rank is equal to the tensor rank. Obviously, in general, that's not the case. The slice rank is always at most the tensor rank, but the converse inequality is false by a lot. But for some tensors, that's the case. And suppose we take one of these tensors. Then for each of the products, AI times CI times EI, there are three. So if you start with a tensor rank decomposition with length k, you can regroup for each term the products AI times CI times EI in three ways, right? You can either put CI and EI together. You can put AJ and EJ together, or you can put AK and CK together. Right? And for all of these choices, so whenever you make different choices, this will give you different slice rank decompositions that again have minimal length, because by assumption the slice rank here is equal to the tensor rank, so these have minimal length. And you can see that here, unlike in the previous example, the total contributions of each of the three parts are usually not the same when you move from one decomposition to another. Now, there's also another way that's different from that, in which we can see that there can be, let's say, widely different slice rank decompositions. say that you have a tensor, an order 3 tensor, for instance, that is defined on k times k times k. So each of the three axes, rows, columns, and I'm not sure what the name for the third is, if there is one usually, but in any case, all three axes, uh, all three axes have length k. Then, if the tensor has slice rank, has maximal slice rank, which here is k, it can never have slice rank more than k, but it can have slice rank k, and as I'll discuss in a minute, that's the case of most tensors actually that are of this type, meaning k times k times k tensors. So if it has slice rank k, you can get three different slice rank decompositions of minimal length by just writing that tensor in a way as the sum of the contributions of each slices. And the direction of the slices is chosen differently for each of your three decompositions. So in the first decomposition, you slice according to the coordinate x. So you get, this slice plus this slice plus this slice plus this slice. Then you slice according to y, and finally you slice according to z. This gives you three different decompositions. Now, these are minimal. So these decompositions, you can always obtain them, but if the tensor has slice rank k, then they are minimal length decompositions because they have length k, and that's equal to the slice rank of the tensor. So this gives you, three radically different minimal length decompositions. And you can ask, of course, but do these tensors exist? Those that are k times k times k and have slice rank k. So one way of answering that is yes, they exist because the identity tensor has slice rank k, and actually that's not trivial to prove. So it's not extremely complicated either, but it's not trivial. It takes a small argument. I mean, it can be done in a page, but it's not immediate. But you can also see this purely from a counting argument, right? If your field is finite in particular, then you can just count the number of possible k slice rank decompositions with length at most k minus one, and this gives you an upper bound for the number of tensors with slice rank at most k minus one. And the proportion of these and when you divide this bound by the number of k times k times k tensors, that tends to zero. So this tells you that a random k by k by k tensor will have slice rank k when k is taken to be large. Now, in the last two examples, I've taken, I've in a way chosen the kind of tensor I took specifically to make, the construction work correctly. But there are also systematic ways that work for all tensors, rather than some carefully chosen ones. So suppose that you have a tensor with that slice rank that admits that as a slice rank decomposition. Okay, suppose you begin with this expression. Do you see a way of modifying this expression to reliably obtain a new decomposition? So that can be done by, in a way, playing on the sort of inherent ambiguity, if you like, of the decomposition, in the sense that if there is a way of systematically adding a contribution, adding at least some types of contribution to some terms and subtracting the same in other terms. So for instance, if you look at a contribution of the type AI tensor Cj tensor E for an arbitrary function E, then this can be done, right? Because you can add Cj tensor E to your function Bi, and you can subtract AI tensor E to your function Dj. and you've just added AI tensor CJ tensor E to the first term, and you've subtracted AI tensor CJ tensor E to the second term. So the total remains the same, but your terms have now changed. So so if the original, in particular, if the original decomposition had minimal length, your new decomposition still has minimal length. So that's a rather systematic way. So that's a systematic way. Now, as I've said, E can be chosen arbitrarily it's an arbitrary function from 1, 2, up to n3 to f. This means in particular that if n3 is very large, then this gives you a very large number of decompositions. And this construction is why it is not true. It is not true in general that if you have a tensor with that if you have a tensor with bounded order, so even for order 3 tensors like this, it's not true that if you have an order 3 tensor with bounded slice rank and and defined over a field of bounded size, then it has a number of slice rank decomposition that is bounded in a way that just depends on the slice rank and on the field size. Because you can, for instance, have A of x, B, you can take here R to be 1, S to be 1, and T equals 0. So you can have a tensor of the type A of x, B of yz plus C of y, D of xz. And you take any function E and the number of, and you do this, you add, you replace B by B plus A tensor E, and you replace D by D minus, so you replace B by B plus C tensor E, and you replace D by D minus A tensor E. If you do that, then this gives you a new decomposition, but the number of possibilities for E is unbounded. So and even if the field has bounded size. And you see this tensor already has slice rank 2. It's not true that it has a bounded number of minimal length slice rank decompositions, even if you make an assumption on the field size. Now we can take this construction a little bit further. So here what I've done is add and subtract a quantity of the type AI tensor CJ tensor E, where the AI and the CJ were already present in the original decomposition, and E was a new arbitrary function, and this made this product in a way, if you like, compatible or factorizable both as a first term or as a second term. But we can, as I said, go a little bit further still and make it compatible with all 3 terms. We can take it to be AI tensor CJ tensor EK for some choices of of I, J, and K. And then whenever you have any 3 coefficients, lambda 1, lambda 2, lambda 3, which add up to 0, and you replace BI by BI plus lambda 1 CJ tensor EK, you replace DJ by DJ plus lambda 2 AI tensor EK, and you replace FK by FK plus lambda 3 AI tensor CJ, then what you've done is, you've added lambda 1 times AI tensor CJ tensor EK, then you've added lambda 2 times that same tensor, and you've added lambda 3 times the same tensor. So whenever lambda 1, lambda 2, lambda 3 add up to 0, you haven't changed the total by doing that operation. So I presented it as a new, as a new systematic way, distinct from that of the previous slide. But in a way, this transformation that we just described, it reduces to doing 3 of the previous transformations. So this is not genuinely a new transformation in a way, except for the fact that it's done in 1 step instead of more steps. But as I said, fundamentally this reduces to the previous transformation. But this is this is an observation that will spring to the mind, I think, pretty quickly if you ask yourself what you can do as in terms of systematic transformations. So it's one thing to note. So even if it does reduce. Now in the last five slides, what I've done is to enumerate or describe ways in which we could have several substantially different slice rank decompositions with minimal length for the same tensor. And of course, once we've seen this, are there more ways, or is there a limit to how this is about, to which extent can this be done? Is there a result in the converse direction, which says that, in a way you cannot have too many decompositions in the same way that we had for matrices, right? Because what we had for matrices at the start was we said, yes, we can make changes of bases, but up to a change of basis, there is only one minimal length decomposition. And for tensors, so for the slice rank of tensors, can we have an analog of that? And the one main result in this work is that, in a sense, yes, up to that class of transformations that I described here, suitably generalized, for higher order tensors. But for order 3 tensors, it's actually just that class of transformations. So maybe it's a little bit easier if I first speak just about the case of order 3 tensors. So for order 3 tensors, up to that class of transformations, really there is only a bounded number of possible slice rank decompositions if the slice rank is bounded and the field size is bounded. Now, what's the structure in a way of the decompositions is that, so the structure of decompositions is once you fixed the slice rank and the field size, you have a bounded number of possibilities for the one-dimensional functions. So in the case of order 3 functions, in the case of order 3 tensors, this would be the functions, AI, Cj, and dk. So you have only a bounded number of possibilities for the functions in a single variable. Now, as I've explained, you can change the two-dimensional functions in many ways, right? As we've seen on that slide, while keeping the one-dimensional functions the same. So it's not true that for the two-dimensional functions there's only a bounded number of possible decompositions. But one thing that is true is that once you fixed the one-dimensional functions, then the only ways of generating new decompositions obtaining new decompositions from an existing decomposition, while keeping these one-dimensional functions the same, is to do this kind of transformation. By the way, yes, so this kind of transformation, I described it for the two first terms, but of course, you can take the first and the third term and the second and the third term. But what I'm saying is for a fixed choice of the one-dimensional functions, the only ways of changing the decomposition purely by modifying two-dimensional functions is to make this kind of transformation. There's no more freedom for the two-dimensional functions than that. Once the one-dimensional functions are fixed. But because for the one-dimensional functions there are only a bounded number of choices, this is not that much of a problem, right? Because what we're saying fundamentally is we're partitioning the set of decompositions into a bounded number of sets. And in each of these sets, the one-dimensional functions are the same. And the two-dimensional functions, or the d-1 dimensional functions in the general case, are just obtained in the case of order 3 tensors, this kind of transformation that I described here, and for higher dimensional tensors, a generalization of this that might be, a little bit complicated to write formally, but that is still clearly in the spirit of that. Right. So this is what I've just said, right? So the first point is the first point to drive home is the number of possibilities for the one-dimensional functions is bounded, and once these are fixed, you can only modify the functions in the remaining variables by making the transformation that I just described. This, by the way, is true also. This second point is true also if the field is finite. So if the field without any assumption of the field, the second point is true without any assumption of the field. Right. So I could go on, of course, and start describing the proof, but I think we've run out of time, so I think I'll stop here. Thank you very much.